Now we're going to take the information that we learned in the previous video about ghost butane interactions that can exist when you have methyl groups and other groups, of course, attached to cyclohexane, and we're going to use that to solve a problem. So before we get into this, we need to review a few terms and learn a new term. First of all, I want to remind you about isomers. So if you have two or more molecules that are related to each other as isomers, remember that means that they have the same molecular formula. We've already seen previously constitutional isomers. Because they're isomers, they have the same molecular formula, but a different, what we would call, connectivity. Now let's slip down below here. Connectivity, to remind you, is the order in which atoms are bonded in a molecule. So all it tells us, connectivity only tells us what order the atoms come in. It doesn't tell us about their particular spatial arrangements. So no information about spatial arrangements, and that'll make sense in just a second if it doesn't now. So if we want to think about spatial arrangements, that's where the whole idea of stereochemistry comes into play. So if you have two or more molecules that are related to each other as stereoisomers, then because they're isomers, they have the same molecular formula. Stereoisomers are going to have the same connectivity, unlike constitutional isomers. So same connectivity. So what's different about them, what distinguishes them from each other, is that the atoms in each structure are arranged differently in space from the atoms in the other structures. So in our next packet of notes, we're going to talk in great detail about stereochemistry, but for now, let's apply this to these cyclohexane chairs that have some methyl groups attached to them. So let's look at an example or two. So what we're going to do is start out with a skeletal formula, and we're going to show the methyl groups using wedges and dashes. Okay, so this one has two methyl groups, and they both are joined to the cyclohexane ring itself through wedge bonds. In the context of the cyclohexane, that wedge means up. Okay, so remember that a bond coming off of a cyclohexane ring is either up or down. The wedge tells you that it's up. So let's number carbons. So 1, 2, and 3. And now let's convert this to a chair. So for my first chair, I'm just going to pick any carbon to be carbon 1. It doesn't matter, and you'll see why in just a second. So there's 1. The thing that matters, although it doesn't particularly in this case, but in general, the thing that matters is maintaining the direction of numbering the ring. So I numbered it, and this was arbitrary. I'm not trying to name the compound. I numbered it in a clockwise direction. So whatever I pick as carbon 1, which again, for the first chair is an arbitrary selection, I'm going to number clockwise from that position. Now the skeletal formula tells me that at carbon 1, there's a methyl group and it's pointing up. So I look at the template, I look at which carbon I labeled arbitrarily as being carbon 1, and figure out what is the up bond according to the template at carbon 1. And if you said it's an axial bond, you are correct. So now we move over to carbon 3, which the original picture of the molecule, the skeletal formula, told us that there was a methyl group at carbon 3 that was also up. So we look at our template, at carbon 3, the up bond is also an axial bond. Now, if we were to draw the chair flip for this, here's how we do it. Okay, so carbon 1 in our original chair, the methyl group is axial and up. That means that when the chair flips, that bond is going to be equatorial and up. So what we need to do is, in our new template, the one that's shown to the right, find a carbon that has an equatorial up bond. There's going to be 3 of them, and I've highlighted the 3. So you can put the methyl group at carbon 1. Carbon 1 could be any of those 3, as long as when you put in the next methyl group at carbon 3, you maintain the direction of numbering. This is true for any time you do these chairs from a skeletal formula. So let's pick the one that was right next door to the one we started with. So that's this guy here. So that's going to be carbon 1. And we're going to number clockwise to maintain consistency. And the other methyl group that was at carbon 3, in our original chair, that was also axial up. And so we would expect that that bond would also become an equatorial up bond. So if we've done this right, then in the chair to the right, to the far right, at carbon 3, according to the template, there should be an equatorial up bond. And in fact, the up bond is equatorial at that position. Okay, so notice then that the wedge, and as we'll see, the same thing is going to be true for the dash, the wedge tells us nothing about axial or equatorial. All it tells us is that those bonds are going up. So the wedge and dash notation gives 0 information about whether those are in axial or equatorial positions. That's why I said when I drew the first chair that it didn't matter which carbon I picked to be carbon 1, because I'm going to get the other possibility when I draw the ring flip. Okay. Now we're still trying to get to this idea of stereoisomers, so let's look at what's going on here. We have 2 methyl groups, and they're on the same side of the ring. They're both up. So this would be the cis isomer, meaning that the groups are on the same side of the ring. It doesn't matter if they're both up or both down, both of those qualify as being cis. Okay, now let's look at the other possibility. So now we still have 2 methyl groups coming off of the ring, but one is a wedge, so we know that that one is going up. And the other one is a dash. The dash means that the bond is going down. When we have a dash line coming off of a cyclohexane ring, that bond is going down. Okay, so let's go ahead and draw some chairs from this. So again, from a skeletal formula, let's number our carbons. From a skeletal formula, you can choose carbon 1 to be anywhere. So I'm just going to choose the same one I did before. And the skeletal formula tells me that the methyl group at that carbon is up. And according to the chair template that I just drew, that would be an axial bond. Numbering in the same direction that I did in the original structure to maintain consistency. The reason you want to maintain the consistency is because you can accidentally draw a different stereoisomer than the one you're intending to draw. So you always, always, always need to draw all the structures by numbering in the same direction. So at carbon 3, what the skeletal formula tells us is that the bond is going down. So I look at my template, and at carbon 3, I recognize that the bond that's down at carbon 3, as I've labeled it, is an equatorial bond. So I put that in. Now let's do the ring flip. And now it matters which carbon we label as 1, just like the example above for the cis compound. So carbon 1, because the methyl group at carbon 1 started as axial and up, what we select to be carbon 1 in the ring flip has to have an equatorial up bond. Well, that's what we saw in the previous structure. And so we could really put that methyl group and assign carbon 1 to any of the highlighted carbons. So again, I'm just going to put it at this one and then number the ring, maintaining the clockwise direction. And then what we had in the original chair was an equatorial down methyl group at carbon 3. So after the ring flip, that's going to become axial and down. So if we've done everything correctly so far, then at the template on the far right, the down bond at carbon 3 should be axial. And in fact, it is. Okay, so these would be the two chairs. This is an example of what we would call the trans isomer. One group is up, the other is down. So they're on opposite sides of the ring. So now what we're going to do is take all of this information and we're going to assess the relative stabilities of a pair of the substituted cyclohexanes. So that is our next task. And we're going to make a little laundry list of the things that we need to do. So to assess the relative stabilities of a pair of substituted cyclohexanes, this is what we're going to do. So just like we did above, so I drew those two chairs for each of the structures to show you how it was done, to show you how you would draw a chair from a skeletal formula. So that's what you're going to do first, is to draw both chair conformations. Of each molecule. So you'd be comparing a cis and a trans, just like we did above. But the thing that we didn't do above, that we're going to do in our next exercise, is to assess all the sources of strain present in each chair. What that means is you're going to look for the Gauche-butane interactions. So we'll say GB for Gauche-butane. So you're going to identify those using the three patterns that I showed in the previous video. Once you have them, total up the strain energy for each chair. And finally, compare the lowest energy chair from each molecule. That will give us the difference in energy between the two molecules. And so finally, and this can't be stated enough, as you might have noticed, always, 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 when you're drawing sets of structures like this, maintain the same direction of numbering. For all the structures you draw for a particular molecule. Now that seems simple enough, and you might say, okay, yeah, I'll remember that. But many, many people don't. And what happens is that they end up changing the direction of numbering. And when that happens, they open themselves up to drawing a completely different stereoisomer than the one that they want to draw, and they lose points as a result. So really, really, really important to always have the same numbering direction for a particular molecule. Now, once you switch to a different molecule, you can switch the numbering order as long as you're internally consistent. So all the structures for a particular molecule you want to number in the same way. And the other thing is you don't have to number them in a way to name them. So we're not necessarily talking about IUPAC locator numbers here. We're just saying number the carbons in the ring so that you have points of reference and keep those points of reference numbered in the same direction. Okay, so let's do the exercise. We're going to do this on the next page. So we're going to compare the energies of cis and trans 1,4-dimethyl cyclohexane. So on the previous page, actually, we looked at cis and trans 1,3-dimethyl cyclohexane. So now let's do these guys. Okay, so the first thing, let's look at the one on the left. And I'm just going to redraw it so that we have a little more room to work. And is this the cis or the trans isomer? So hopefully you are saying cis. And if you are, then you are completely correct. So this is cis, and the other guy is trans. Okay, so I've gone ahead and numbered the ring. And so now let's draw chairs. So when you start out with your very first chair, just select any carbon to be carbon 1. So I'm arbitrarily picking the upper left one, but it could be any of them. I numbered the original structure clockwise, so I'm going to do that again here. Even in cases where it doesn't matter, you still want to get into the habit of doing it this way. And now let's put on the groups. At carbon 1 in the skeletal formula, I see that the methyl group is pointing up. So according to the template, the up bond at carbon 1 that I've selected is axial. So there's our first methyl group. And then at carbon 4, the methyl group there is also up. So I look at the template, and knowing what the template tells me, I know that the up bond at what I have labeled as carbon 4 is an equatorial bond. So I put that in. So that's the first chair. Let me move this 4 out of the way. There we go. Okay, now let's draw the other chair. And now remember, it's going to matter where carbon 1 is. So carbon 1, the methyl group started in the first chair that I drew, axial up, meaning that it has to be equatorial and up in the new chair. And again, there are going to be 3 possibilities for that. You could make carbon 1 any of those 3. But let's just make it this middle one here. Number the ring in a clockwise direction, and then put the methyl group in. So the axial methyl group in the first chair after the ring flip became an equatorial methyl group, but they stayed up. At carbon 4, our up equatorial bond should convert to an up axial bond. And so we look at the template. If we've done this correctly, then at carbon 4, the up bond should be an axial bond. And that is true. It is. Okay, so that's the other chair. Let's repeat this for the trans the trans isomer, and then we'll start assessing the energies and looking for the ghost butane interactions. Okay, so arbitrarily I'm going to start numbering the ring. And notice again that I chose to number in a clockwise direction. I could have chosen counterclockwise as well, as long as I'm consistent throughout my drawings. So we'll draw the first chair. And remember, for your first chair, the first chair that you're drawing from a skeletal formula, it doesn't matter what you pick as 1, because in the chair flip, you're going to pick up the other opportunity, or the other possibility, I should say. So I'm just going to go with what I've been doing, which is to make the upper left carbon, carbon 1. But again, that's up to you. It could be any of them. And so in the skeletal formula, it tells me that the methyl group at carbon 1 is going down. So if I look at the template that I just drew and the carbon that I've selected to be carbon 1, the down bond, according to the template, at carbon 1 is equatorial. So there it is. And then the skeletal formula also tells me that the methyl group at carbon 4 is up. And according to the template in the chair that I've drawn, the up bond at carbon 4, as I've labeled it, is also an equatorial bond. Okay, go ahead and pause the video and draw the chair flip for this. Once you do that, remember that carbon 1, we need to find a carbon in our new template that has an axial down bond. There's going to be 3 of those. So let me draw this in. So the carbons that I'm highlighting are the carbons in this template that have axial down bonds. So I'm going to make this carbon 1. And then number in the same direction that I've been numbering. And so in our original chair, the methyl group at carbon 1 started at an equatorial down bond. After the chair flip, it's axial down. Carbon 4, the methyl group started in the original chair as equatorial up. In the chair flip, it's axial up. Okay, so we have drawn our chairs. We've drawn both chairs for each of the molecules. So now what we're going to do is assess the Gauche-butane interactions. So this is where we would want to look for those patterns that we went over, the 3 patterns. So let's start with this first chair. Okay, so the first chair in the cis compound, or the cis isomer. So we have an axial up methyl at carbon 1. So we'd be looking for the axial up hydrogens on the same side of the ring. Those occur at carbons 5 and 3. So we have Gauche-butane interactions. Remember, we draw the line from carbon to carbon in the pattern, from that methyl group to carbon 3 and carbon 5. The equatorial methyl group is not in any trouble at all. Okay, so that doesn't fit any of the patterns that we looked at. So we just have the 2 Gauche-butane interactions here. So 0.8 times 2 is 1.6 kcals per mole. In the other chair, we also have an axial methyl group, and so we would be looking for Gauche-butane interactions to occur between the hydrogens on that methyl group and the axial hydrogens on the same side of the ring. So because that methyl group is pointing up, we'd be looking for the axial up hydrogens, and they are at carbons 2 and 6 as I've numbered the ring. There are no other Gauche-butane interactions because we don't see any of the other 2 patterns that I described to you previously. So this one also has 2 Gauche-butane interactions, each of which carries an energy of 0.8 kilocalories per mole. So the total strain energy for this chair is 1.6 kilocalories per mole. Now let's turn our attention to the trans compound. In the trans compound, in the first chair, the one with the two equatorial methyl groups, neither of those is involved in any gauche-butane interactions. So that chair has zero strain energy. By contrast, in the other chair, both of the methyl groups are in axial positions. So we need to look for the axial hydrogens on the same side of the ring as each of those methyl groups. So let's start with the down methyl group at carbon 1. There are also two down hydrogens. Those are at 3 and 5. So we have gauche-butane interactions between the hydrogens on the methyl group that comes off of carbon 1 and the axial hydrogens on the same side of the ring, that is the other down axial hydrogens. So we have two gauche-butane interactions there. If we look at the methyl group that's pointing up and in an axial position at carbon 4, it too is going to be involved in gauche-butane interactions with the axial hydrogens that are on the same side of the ring as it. Those would be coming off of carbons 2 and 6. So we have a total of 4 gauche-butane interactions, which gives us 3.2 kilocalories per mole of strain energy for this chair conformation. Okay, so where are we on our checklist? We've drawn both chairs for each molecule. We've assessed all the sources of strain for each of the chairs. And so now what we're going to do is compare the lower energy chair from each molecule. Why do we compare the low energy chairs? That's because more molecules are going to occupy those conformations than the higher energy conformations. So in the cis, both of those conformations have strain energy of 1.6 kilocalories per mole. So there's no getting around it. Okay? Whichever one we look at, we still have 1.6 kilocalories per mole. But in the trans, the vast majority of these molecules of trans 1,4-dimethylcyclohexane molecules are going to occupy the chair conformation that's shown to the left, the one that has no strain. So we would subtract 0 from the 1.6. That gives us an energy difference between the two of 1.6 kcals per mole. So this is the difference in energy between the two stereoisomers. Okay, so which numbers do you plug in here? Is it always cis minus trans, or could it be trans minus cis? That just depends. It's going to be the larger number minus the smaller number, which is what we did here. Okay, let's look at one more thing relating to the substituted cyclohexanes. And this is something called a 1,3 diaxial interaction. So let's pull this name apart and see what it means. 1,3 is an example of something you'll see a lot. So you'll see labels like 1,2, 1,3, 1,4. Those are probably the most common ones you'll see. 1,3 means that you have two groups and they're attached 3 carbons away from each other. So if you have a 1,3 pattern in a molecule, that means that you're referring to two groups that are 3 carbons away. So the groups are attached 3 carbons away from each other. So we can see that in the picture down below. So numbering the carbons, one methyl group is attached at the first carbon in the pattern, the other methyl group is attached at the third. The term diaxial means that both of the groups are in axial positions. And finally, as we saw with the ghost-butane interaction, the term interaction implies that there's strain. It implies that there's some kind of strain going on, probably that groups are getting too close to each other, so this refers to steric strain. So a 1,3 diaxial interaction means that you have two groups at the 1 and 3 positions. They're both in axial, they both occupy axial bonds, and there's some sort of an unfavorable steric strain going on between them. Okay, so the main example of this is the one shown here, and this is called a syn-pentane interaction. So unlike a gauche-butane interaction, which has 4 carbons involved in its pattern, a syn-pentane interaction has 5. So we're going to abbreviate this as SP. And so here's the first carbon in the pattern, and the hydrogens on that methyl group are too close to the hydrogens coming off of the other methyl group, which would be the 5th carbon in the pattern. So 1, 2, 3, 4, 5. So it's a 5-carbon pattern where the 1st and the 5th carbons are lined up with each other. But we can't call them eclipsed. They'd have to be on adjacent carbons to be eclipsing one another. So instead, we call them syn. Now notice that in this particular example, the syn-pentane interaction is only one of the sources of strain. You also, because you have axial methyl groups, you have ghost-butane interactions between each of those methyl groups and the axial hydrogen that's on the same side of the ring. So there's 2 ghost-butane interactions in addition to the syn-pentane interaction. So a question that comes up a lot, so I'd like to address that here, is the following. So I'm just redrawing the molecule from above. And the question here is, why is that not a ghost-butane interaction? The reason for that, remember, is that the methyl group at carbon 3, in this case, to experience a ghost-butane interaction, you have to have an axial hydrogen on the same side of the ring. Okay, so from that methyl group to carbon 5, at carbon 5 you do have a hydrogen that's too close to the hydrogens on the methyl group that's coming off of carbon 3. You don't have a hydrogen coming off of carbon 1. Instead, you have a methyl group. So that takes this out of ghost-butane land and puts it into syn-pentane land instead. So the syn-pentane interaction involves the hydrogens on the methyl group at carbon 1 with the hydrogens on the methyl group at carbon 3. They get pretty close, and so this is a more severe interaction. That is to say, it causes more strain than just a ghost-butane interaction. But be careful with confusing the ghost-butane and the syn-pentane interactions.